All right, everyone, we're going to start the afternoon session. I think Jim Doyle, are you on the line?
Yes, I am.
How you doing, Jim? Looks like we have you listed as one of the co-chairs. So is there anything you wanted to say before we go into the first talk?
I will defer to VJ. Is VJ there?
Unfortunately, VJ is not with us this week for the first time since HFIP was created. He is at a WMO meeting. So I will,
okay.
I can handle it for him. But our first presenter is Jamie Rome. You guys may or may not know him. He's from the National Hurricane Center. So Jamie, come on up.
All right, so the session before gave us a great snapshot of some of the challenges. So my job was to sort of, recreate that a little bit in more of a synopsis type format. I just wanted to, again, go back to this. This is what social science is saying. For those of us on the forecasting side of the spectrum, where we have to, did I do that? To where we have to go from a forecasting perspective to make our message more actionable. We won't spend a ton of time on this, but I just wanted to highlight some of the items here since I blew through it quickly in my earlier presentation. Identify ways to localize and personalize TC information. This is probably one of their biggest messages that they're telling us, is people have to envision the threat in their home, in their backyard. If you haven't seen these statistics about how bad the general population is with a map, have you seen these, Craig? You've been doing, yes, it's bad. It's bad. So the point of this, if you haven't seen these surveys, is people cannot find themselves on a map, much less find themselves on a map of a hazard. So they have to have a way of localizing and personalizing the threat. This is why TV meteorologists do so well in the ratings during hurricane events. Survey after survey after survey shows that 80 to 90% of the population get their weather information during a hurricane from their local TV meteorologists because they are localizing and personalizing the risk. Improve the accessibility of TC products and services. And I think with this group, this is, you already do this really, really well, but it is not the case in all groups. There exists a subset in the United States that feel that the general population cannot handle risk information, that somehow the general population is going to assess their risk and just run out and like in the streets and like mob everyone. Craig, you know this one too. How many of you would be shocked to know that evacuation zones are not readily available or easy to find? That is an implication that people are scared to make information readily available and acceptable. As we move to a risk-based approach, we have to be willing to make that risk information readily available and accessible. People search for different types of information and validate the information, and we should be okay with that. We should be okay with if we say something to a population that they go and crosswalk it with their neighbor or their pastor or whomever. That's just how the mind works. It's going to search for and validate that information, and if it hears it the same way over and over again, that's what builds confidence. And that's why consistency of message is so important. Now, this one is relevant to this group because we live in an era now where there's a flood of information. You just pull up Twitter in the middle, I'm sorry, the artist formerly known as X, formerly known as Twitter. And not only can you get different messages, you can even get a cone not issued by the Weather Service. And so as people are trying to validate and figure out what to do, they're paralyzed by all this information that's out there. Timing information is critical for decision makers. So it's not just the hazard, it's when the hazard starts and ends. This is really, really important for emergency managers. Timing is more important than you could possibly imagine. How many of you would be shocked to know that evacuation decisions, one of the most important data sets for evacuation decisions, is the onset of tropical storm force winds? Is that surprising? Bridges, you don't want people evacuating in the middle of wind. You know, we're all enamored with the eye and that sort of stuff, but there's other information out there that is incredibly important. Uncertainty information is important to communicate, but not always communicate it well. I have this saying, the problem with communication is the illusion that is occurring. And let's face it, as physical scientists, we're trained to communicate with each other. By our very nature, this venue is what's most comfortable, right? We mean absolute error, right? That's where we're most comfortable. And we're increasingly in a world where we're communicating to people that have no science background. And it's tough. We need more work on communicating uncertainty. This one's probably going to be upsetting for people. Graphical tropical cyclone products are important, but some need to improve their depiction of risk and or uncertainty in those products. And this is not me, this is social science findings. So this is not my opinion. These are findings from social scientists on how to improve risk communication and perception. So graphical product design is really, really, really important. And then we'll get to some misperceptions here. There's a misperception amongst forecasters and partners that the public does not understand uncertainty information. That is resulting in people not wanting to communicate uncertainty information. But, and I don't have it in front of me, but if anybody's interested, just email me. There's actually a research paper that found that not only do people trust probabilistic information more than deterministic information, they make better decisions on probabilistic information. And I think the reason behind it is, and I'm going to guess here, is that the public is smart enough to know that there's uncertainty in the forecast. And if we don't tell them that, they think we're withholding, right? We're not giving them the full story. And there's a misperception in emergency management that emergency managers have the same numeracy. Numeracy is a term, understand and comfortable with numbers and probabilities and that sort of stuff, that they're on the same level. So sometimes we make the mistake of talking to emergency managers like we talk to each other. So anyway, there's that, and you'll probably see this slide again. So now, with that, what are our priorities in terms of gaps? Prediction, not only prediction of, but the communication of rapid intensification. What does a forecast, you're in the hot seat. And I assure you, if you forecast the Hurricane Center, it feels like a hot seat. And you get a probability of RI of 33%. What do you do? What do you do? Do you explicitly forecast it? Do you not explicitly forecast it and put some verbiage into discussion? Do you explicitly forecast it and say, but there's a probability it won't occur in the discussion? How do you handle that when you have a low probability of a high impact event? Now, let's say on the public service side of things, you err towards, I'm going to serve, I'm going to communicate the risk, and you communicate that it's going to happen because it's a high impact, and then it doesn't happen. Now everybody's mad. How do you deal with that in the days after? Quantifying and communicating forecast uncertainty. Like, I think the forecasters know abstract about uncertainty, but how do you quantify that? Like, how do you Is there an uncertainty metric? You know, these sorts of things are what are perplexing our forecasters. The rapid expansion of new forecasting tools and observations. This is one that's going to be near and dear to our forecasters. We love all these new tools, but our staffing levels are not increasing. And so as a forecaster, they are stuck with trying to figure out how to analyze all this new stuff, and their workload is not going down. In fact, the workload is going up, and they're being hit with more and more models, more and more observations. So, which leads us into the next one. What is the role of AI for the forecasters going forward? Is it to sift through all of this new information and sort of tell the forecasters where to prioritize their time? Is that the role of AI? That's a relatively untouched area. In the visualization of ensembles, this is another one that's going to be near and dear to our forecasters. As the number of ensembles increases, it is impossible now to sit there and look and critique every single ensemble member. So what are the metrics to look at those ensembles and present that information to the forecasters so they then know where to dig beyond that? You know, I can remember when just 4 or 5 ensemble members was like, that was great. Now what do we've got? You know, we've got probably over 100, I'm guessing, right? And growing exponentially by the minute. The way that forecasters look at ensemble information is changing, and I'm not sure that we have the visualization techniques and software yet to allow us to fully take advantage of that new arena. So that's it on time. I think I'm up at time. I just wanted to give you a quick snapshot of where we are from a forecaster's perspective on our priorities and challenges. Again, thank you so much.
Thank you, Jamie. I want to make, I'm going to eat some of our time here. I apologize in advance, but I wanted to let you guys know that they are having issues with the Wi-Fi. They told us to use the Hilton Honors Wi-Fi and then put in the code capital GOL, and that should be able to get you on the network.
Okay, so for our next presenter, I'll introduce Zujin Zhang at AOML and also with his collaborators at EMC.
Thank you, Bill. Thank you, Will. This work, you know, I'm a bad guy to talk about the bad things in the model. So I can talk the success HAFS this year. I'm going to point out a few failure we have. Next slide. This is really important slide I have to show here. You know, this is the whole team work on this. So not me. I didn't physically do a lot of work. So this is our team here. Next slide. So you will see this slide over and over in next several talks. They talk about successful. So move to next slide. This is the 4 basin we are running. The North Atlantic, East Pac, West Pac, actually 5 basin. You know, North Indian Ocean and the Southern Hemisphere. Next slide. Okay, now this is the real things start. So we look, here I focus on the HAFS A. So the line we compare, everything compare is HAFS A. So below the line, you see the skill is worse than HAFS A, and above the line is better than HAFS A. So here is fully basing, we do the verification. In terms of the track, Atlantic is fine, the same conclusion with John Koslagi just showing, but the intensity, HAFS A is not there. You know, several model better than HAFS A. On the East Pac, we almost have the reverse. Intensity is better than any other regional model, but the track is almost like you know, compatible. In terms of West Pac, we can see HAFS A is doing fine. Both track and the intensity. Next slide. So now I'm going to talk those tough stone. Lee, in track, we are doing fine. It's only 50 knots, 72 hours. That's John just showed that. I didn't do the stats, but here we can see however, the intensity, if you see, can we see this? Okay. Yeah, if you see here, first we have delayed rapid intensification. It's about 12 hours delayed. Then also not weakening. So after that, not weakening. So that is the problem we want to look into there. Almost every cycle, we have the same issue, is the delayed rapid intensification. So that is what we need to look into. Why? Even though, yes, we can produce the intensification. So rapid intensification, but delayed. Whichever the cycle is, always have the delayed rapid intensification. Next slide. So here you see the verification. I'm going to skip this to next slide. Okay, so this one I did one more experiment that is puts the uniform 3 kilometer use GFS without vortex initialization. You see the line is here, the blue line. Both track and intensity is getting better, especially the later on. Certainly, don't trust this line yet because it's 3 kilometers weaker than 2 kilometer stone. So that's why we never really get to the 170 knots. So that's why the verification looks better. So verification sometimes give you some false information at some point. But track definitely, if we have the higher resolution 3 kilometer for the outer domain, you'll see the tracker is getting better. So our high resolution always showing the similar tendency. The track is getting better. Next slide. Okay, so this is what I show in all those lines. You'll see the this is fixed to the operational model. This one is without DA but have the vortex initialization there. You'll see here it's always like overshoot of the intensity, and this one is used with DA, with the ENCAP DA, but this one have GFS only, no DA. And you see DA not help us for this problem too. So at this moment, I'm just point out the point, the problem here. Okay, next slide. So if you look, I just mentioned that the zoom in this. All these like ensemble member, the ensemble talk, they will talk about that. But I want you to focus on the 2 points I point here is that this tendency about 12 to 18 hours delay of rapid intensification. It's showing every member plus our deterministic forecast, some even worse. So this is the HAFS system. Now include everything in all kind of configuration have the same tendency, about 12 to 18 hours delay. Next slide. So even close to the rapid intensification, six hours before, you still have this kind of tendency. So this is one of the problems we don't know why the model needed have this kind of tendency that 12 hours to 18 hours delay. Okay, next slide. Okay, so yeah. So also the initial condition, also we have the issue here. If you see that the quick the quick spin down here. Next slide. Okay, now we go to Otis. So Otis has the problem, you see all the track. This is the best track, working back best track, and all the forecast is going to this area. And you can see only for HAFS A, only one cycle doing kind of rapid intensification, and for HAFS B, have one cycle or probably two, have some kind of rapid intensification. Go to the next slide. So this is what I see. The ocean part, sometimes we think it's the ocean has a big impact of that. But when we see this two cycle on 12 hours forecast, you'll see the storm going to this area. So it intensify quickly. But go to the next slide. We have 48 hours. The storm, the actual position, and the forecast 40 hours before initial time, 48 hours before, you have almost 2.5 degree differences. So it's going to the cold area, coldest SST area. This is about 27, and this area is more than 29. So that's one of the reasons not to intensify the storm at all. Okay, next slide. So this is, I just mentioned, the Doksuri in Westpac. We have the tendency, all NCEP model, we have the tendency go to the right. So this is one of the problem in Westpac. And also, I think Levi didn't mention this storm, that this storm have the second intensification, which not showing in our model. So this is all the issue so far we can see. Final slide. So this is the summary here, and I'm not going over go over this, and you can read it online for the summary what I find. Thank you.
Yeah, thank you, Zhujin, for that great summary. Yeah, I think it's important to look at the bust and missed forecast cases too, so we can try to identify those model problems and what went wrong. So next, we have Julian Hemming from the UK Met Office. Julian, are you on the line?
Yes, I'm on the line. Can you hear me?
Yes, we can hear you. Take it away. Thanks.
That's great. Well, thanks very much for giving me the opportunity again to present to this conference. As you can see from the title, I'm going to do a brief update on aspects of Met Office global model performance and forthcoming changes. But mostly, with the theme of this session, I'm going to be looking at picking out some challenging storms for global models, not just Met Office global model, but some of the other global models as well, the ECMWF and GFS and their ensembles, and just highlighting a few challenging storms as we've already been hearing about a bit today so far. So if you can go to our next slide, please. So firstly, looking at the Met Office global model performance in 2023. Now, as I reported last year, the Met Office deterministic and ensemble global models are now coupled to the ocean. And there are also some major physics changes were made. It was over a year ago, about a year and a half ago now, to better handle the timing and characteristics of convection. This gave better general numerical weather prediction scores, but tropical cyclones have become a lot weaker, which is the downside of this this change. You can see that in these statistics, or the charts here, which are showing for the Northern Hemisphere 2023. Top right actually shows the last 6 years performance for central pressure bias. You can see the top two lines, the dotted lines, are 2022 and 23, showing that we now have a weak bias, which wasn't there in previous years. And the bottom right is showing the tracked forecast errors. They're generally, it's a long time sequence there, so obviously the current year is right at the far right hand side of that. And the track errors are, I'm looking at the whole of Northern Hemisphere here, so as not to kind of have the influence of one or two storms affecting the statistics too much. And the errors are near to or slightly higher than previous years. As has been mentioned previously, there has been a kind of spike in Atlantic forecast errors this season, but actually for the Met Office model, it was actually no higher than the spikes which we saw in 2020 and 2015. So there was certainly a spike in the errors in the Atlantic this year. But if you can go to the next slide, I'll start to look at some of the kind of challenging. Oh, sorry. Before I do that, I just to mention the next global model change, which is coming up for the Met Office model. There's further changes to the convection, which will then produce stronger tropical cyclones that recover some of that loss in intensity which we've seen, and it also improves the track forecast generally, and by a small amount, but also the ensemble spread. That new configuration is being run in near real-time trials, and these plots show some of the results from those trials for this year. Bottom left shows the track areas, which shows small differences, maybe slightly better at longer lead times, lower areas. The green is the trial. On the right is showing the central pressure bias, which is showing that strong, well, that kind of weak bias, which is prevalent in the current model, which is the red line there, is reduced significantly, although not totally, by the new configuration. Now that configuration, unfortunately, is not going to be coming up into operations fairly soon, because we have to have a new supercomputer installation before that, and there's been various delays to that for technical reasons. So it's going to be some time before that new configuration is actually implemented. If we can go on now to the next slide, which will show some of the kind of challenging cases which I've kind of picked out. The top one here, actually, I'll explain these plots because there's a few of them around. These show the ensemble and the deterministic tracks for 3 different models: the Met Office model, or the global model, and the MOGREPS, which is the ensemble, which is in the light green. The blue is ECMWF, and the kind of pinky color is the GFS or the GEFS for the ensemble, which you see here in these plots. So the top one is an example from Tropical Storm Cindy, where it tended to be that the Met Office model was weaker for Tropical Storm Cindy, but it was better for the track. And in this case, as you can see, the GFS, the GEFS, was too strong. The far right plot shows the intensity compared to observations, and the pink dotted line is the GFS there. And so in this case, the Met Office model was slightly better for track. Now, if you go down to the bottom, Hurricane Lee, the Met Office model was just too weak for Lee, and as a result of that, I think it tended to pick up on a different steering flow, and it steered Lee in towards the Bahamas, which was incorrect. Whereas the stronger models at the GFS correctly turned Lee northwards. And I think this is an example of where you're getting, obviously the GFS tends to be the strongest of all the models, and the Met Office model the weakest, but it doesn't necessarily mean that it affects the tracks in the same way. You've got examples of here of it going in both ways in terms of which was best for track. Now the next case and the next slide shows Tropical Storm Philippe, which we've already heard quite a bit about today. And then in this top example, one of the early forecasts, obviously here you can see all the models were missing the actual track of Philippe towards the northeast of the Leeward Islands. But in this particular run, and for several of these runs, actually the MOGREPS and the Met Office system did better. Certainly wasn't good, because it wasn't picking up on the actual track, but it was better in terms of the westward progression rather than the strong turn and recurvature, which some of the other models like the GFS, which you see here, was picking up on. And at the bottom, you got some later examples when it was starting to turn, and even then it tended to be the models which were weaker for intensity, which was the Met Office model and ECMWF, which were slightly better on the track, had more of a westward motion before turning north than the GFS, which was too strong and also turned north and recurved too soon. If we go to the next one, Hurricane Franklin shows various challenges for the models. It was difficult to capture that erratic motion of the storm when just north of the Caribbean, and also the extent of the northwestward turn, and as the strengthening started, and the recurvature, and also capturing the rate of intensification. It was a multifaceted, this one, and the models generally tended to accelerate Franklin to the north, and even up towards potential landfall over eastern Canada too quickly. as you can see at the top one. Now in the bottom plot, which is obviously some time later, this shows the kind of extremes which were occurring with the models. So models like the Met Office model tended to accelerate towards the northeast too quickly, with potentially glancing across Newfoundland. Whereas you can see in the blue there, the ECMWF model actually went to the opposite end of the scale and was looping Franklin quite slowly down in the subtropics. Now, in reality, the actual track was somewhere in between those two. And I think a lot of these cases which I've shown do kind of highlight the value of a multi-model ensemble, in that generally it's not one model which is outperforming all the others every run and every case. There are somewhere which doing better than others. And in these cases, when you look at it statistically,
Julian, you have about 2 minutes.
okay, I'm almost there. It generally comes out that the multi-model ensemble comes up with the best prediction if you average it out over the whole season. I think I've got a couple more slides, so that should be just about right for time. Hurricane, a few intensity issues here. Hurricane Lee on the top. This is just showing the Met Office model here. On the top right, the rapid intensification of Lee just wasn't handled by the model. Top right actually shows the operational central pressure predictions, which is in red, and the new version of the model, which is in green. Now, although that's better for intensity, it wasn't able to handle the intensification. And actually, the bottom part of the slide as well shows Hurricane Dora, which, although track forecasts were very, very good, it was a small but intense hurricane, and the global model at its resolution just couldn't handle it. And then you can see there that even though it was generally initialized as quite a strong storm, it just constantly lost intensity through the forecast, consistently run after run after run, which is something that often happens with global models when you're looking at a very small and kind of compact system. If you go on to the next one, I should just about be finishing off now with just a few East-Pacific cases. I've noticed that recently there does tend to be a propensity for all the global models for East-Pacific cases which tend to recurve or turn towards the Mexican coast to have something of a left of track bias. Now, be interested to know what the reasons for this might be, whether it's something to do with the larger scale synoptics. But these are cases from 2022, Kay, Orlean and Roslyn, where the models were all left of track. And if you go to the next slide, which I think is my last one, from this season, obviously we've had Hurricane Lydia as well, which was very problematic in that at the top here, you can see none of the models were really predicting well the kind of 180-degree turn, and didn't have the landfall at all at that stage. And then the bottom part of the slide is a few runs later where the models were predicting that turn towards Mexico, but then again had a kind of left of track bias curving Lydia up towards the Gulf of California. So this seems to be a repeat of that kind of pattern of something of a left of track bias, which models tend to have for storms which are kind of recurving towards Mexico. And I put down the bottom left there. I haven't got any time really now to discuss Otis, but plenty has been said already, and I'm sure that will be in future presentations over issues with Otis, and obviously most notably the failure of models to predict rapid intensification, which we've already heard about. But I think I've run through things quickly. I'll finish there.
Yes. Thank you, Julian. We always appreciate the perspectives from the UK Met Office. It's great that your team continues to collaborate with us on HFIP. So right now we'll turn it over to Linus Magnuson at ECMWF. Are you on the line, Linus?
Yes, thank
Okay.
you. And you can start with the next slide.
Yes.
Yes, so next slide, please. Okay, here we go. So first, a quick update about the operational changes at ECMWF during the past year. And we had our major upgrade in June, where we went to to 9 kilometer resolution for our 50 member ensemble. So now our ensemble is the same resolution as what it used to be our high resolution system. So we run with 50 members plus one unperturbed member out to 15 days ahead. We have a separate forecast data set with 11 members for the past 20 years. Then for the extended range, we introduced a new suite that runs every day for the 0 UTC initial time with 101 members out to 46 days and with 36 kilometer resolution. So that's a big change from what we had before with twice a week extension with 50 members. And also here we have reforecasts with 11 members and out to 20 years with a 36 kilometer resolution. And no change for this year, but just as a reminder that the all-season WF forecast run in couple mode with a coupled ocean model and interactive ocean waves. So next slide. So I will first talk about the prediction of the genesis of TC Tammy. So what you see here is the forecast from the 12th of October, so 7 days before the genesis time. And the symbols you see is from the 21st of October, 12 UTC. So already a week before, a lot of members captured the genesis, and actually the tracker picked up a vortex a long time before it was had its official genesis, because this storm came out from an African easterly wave. So next slide. So if we then step forward in time and look at forecast from the 14th of October that you see to the left, there's a high percentage of the ensemble members that picked up the genesis and also the track of Tammy, although it curved it a bit to the north. However, if we go to the 16th of October, you see that the number of members that had the cyclone decreased a lot. While if we go to the 18th of October, so initialized 1 day before the genesis, it had come back in the number of members that picked up the storm. Next slide. So if we look at the summary plot, and this is produced by Sharam Majumdar, and you will see more of these plots in his talk later today, we can see the evolution of the probability of predicting the genesis when we're approaching the time. And here we use the 25 knot threshold in the forecast to pick up the storm. And 6 to 5 days before the genesis, that we predicted around 70-80% chance. Well, then around day 3 to 4, it dropped down to 50%, and then later on, a day or two before the genesis, it came back. So next slide. So if we just look at the consistency in the IFS model, so in this, so this is now based on just the HFIP model, and what we see here is in contrast the mean level pressure, and in shading the 850 hectopascal wind speed valid for the 21st of October 12 UTC. So we have the shortest forecast from the 20th of October to the top left. And then you can see that we put the arrows that it picked up some sort of cyclonic feature from the 18th, 12 UTC and onward. But you see a number of forecasts that missed this feature, and while it had it on the 15th of October. So also in the HRES showed this drop in the signal from the 16th out to the 17th, 18th. So if we go to the next slide. So I believe none of you have missed the development in the past year of machine learning models. And at the ECMWF, we have been working on our own version, which we call AIFS. And it's trained with ERA 5 data and is initialized by ECMWF analysis. And it's currently trained on 1.1 degree data. So that's the resolution. We have a quarter degree version in the pipe, and we produce this forecast daily, and we put all the maps on the ECMWF website along with the Pangu weather model, GraphCast, and ForecastNet initialized from ECMWF analysis. So what you can see on this slide, which is the same type of plot as the previous, is that all these runs from the AIFS has a cyclonic feature that about being much weaker than it was in reality, because there's a feature of this type of models. It had an incredible consistency in predicting the genesis and propagation of tropical cyclone Tammy. So next slide. And just to show that, I will not go into the details, but this tropical cyclone then posed further issues or uncertainties with, if we look at the forecast from the 24th and what was going to happen in the Atlantic with a possible landfall from Key West up to Ireland. So next slide. So going into the
You got 2 minutes left.
Yeah, thanks. So going into intensity forecasts, here picked up the quote, the good, the bad, and the ugly, and we have seen them before this session. So what I show here in gray is the ECMWF ensemble, which, as I said, run with 9-kilometer resolution. Then we have our HRES and control forecast in red and blue. For some reasons, they are not bit identical, but that also show what uncertainty one can get from scientifically identical runs. Then we also run in our Destination Earth program, which is working on a digital twins, a 4.4 kilometer version of the IFS that you can see in purple. So if we start with TC Idalia, you can see that especially this 4.4 kilometer run did incredibly well with the rapid intensification. And you can see so on the higher end of the 9-kilometer ensemble. While TC Otis has been mentioned in previous talks, also with our 4.4 kilometer resolution, the rapid intensification was missed, and none of the 9-kilometer ensemble members captured it. And then finally, tropical cyclone Lee, we can see the delayed intensification in the 9-kilometer version, as discussed also from the HAFS. However, with the 4.4 kilometer version, it captured the rapid intensification very well, but then it just continued to intensify. And after 5 days, it reached a core pressure of 880 hectopascal, which is quite worrying, especially as these runs are with a coupled ocean model. So we continue to look into these cases with my colleague Mikkel Meyer-Gaber. So next slide.
I think we got to wrap it up now. It's just a summary.
Yes. So yeah, to summarize, we had this drop in the prediction of the genesis for Tammy 2 to 4 days before the genesis. but it seems to be much better handled in the machine learning models, which is we are quite curious and want to understand further. And then that the rapid intensification is still challenging with the 4.4 kilometer model. So what we want to know from the community is what's different, the predictable and the unpredictable cases. So stop there.
All right, thanks a lot, Linus. I'm sure there's certainly plenty of interest in the room here on hearing more about your AI model. And now also we saw this morning how impressive the deterministic ECMWF did this past hurricane season. So thanks for that. And looks like for our next talk, we'll have Fang Lin giving the updates from NCEP.
So apparently I'm another VG, and he said that he really like to be there, but this time has very important WMO meeting to attend. So for those of you who don't know me, I also work at the EMC. Currently I did the physics and the dynamics division. I hope I'm using the right arrow.
The big green arrow.
Big green, oh, I see, okay. So this outline, I first review the performance, GFS and GIFs performance in this year. Then I talk about a little bit about the future systems. So the 2023 anti-triangle intensity verification from the GFS first. So you can say the in terms of the overall and the track performance, ECMWF is the best. If you look at the align track, then the cross track, the major problem with GFS, it has moved too fast, and also has the right of track biases. In terms of intensity, both absolute intensity and also intensity bias, GFS probably is better than the other international models. So in the following slides, I'm not going to focus on the intensity. GFS and GIFs, they all show better intensity than other global NWP models. I focus more on the track part. So this for the Eastern Pacific. Among the 4 international models, EC still have the best track until this 3, and GFS has better track anchor forecast time. GFS moved too slow, and the GFS, the cross track is pretty decent in the Eastern Pacific. For Western Pacific, so GFS is competitive compared to ECMWF. You can do it worse for the Western Pacific in this case. For align track and the cross track, all models have slower and right of track biases. You can see none of them did a good job. And now move to the ensemble forecast system, the GIFs. So first for the alternative benzene, there are also the 4 models, GFS, and this ECMWF, and Canadian model, UK MO model. So for this one, for the ensemble, the EC ensemble is still the best, and it's written. But for align track and also cross track, similar to the GFS, the GIFs move too fast, especially align track at the non-critic forecast time, and also has the right hand side of cross track arrow. Comes also true for other models, but GFS is a particular notch at near forecast time. Again, the GIFs ensemble like GFS has better intensity than other NWP models. So for Eastern Pacific, GIFs somehow is the best this year, given the GFS trouble in many of the cases. gives show the base trend forecast. For the alarm trend, I guess the base trend comes really for this cross trend gives basically no cross trend errors. But it still has a little bit of the moved a little bit too fast and the alarm trend forecast. For Western Pacific, again, the ECMWF model is the best. GFS, like the GIFs, like the GFS, also suffered from this alarm track and the cross track biases, moved too fast, and also had the right to the right hand side of the cross track arrow. A couple of challenging storms. This has been mentioned many times in today's presentations. Philip, you can say here, this is one case initialized on September 25th, the other day, and this HFIP party didn't do a good job. GFS also has large biases. This HAFS A and HAFS B did much better job. Now this GFS and also the Hurricane, the HAFS and also HMAN. This overall average for the entire lifetime for this Philip, you can say the HAFS B as the best track, and GFS is here. And another case, Hurricane Tammy, was mentioned a few times. Again, for this system, for this particular utilization, October 24th, 18 day, and HAFS B, and did I say a marvelous job, and other models have struggled. For the entire lifetime, Tammy collapse did a good job. Did this for the first 4 days, and Chief struggled for this storm. Had the not just trunk arrow.
Got about a minute.
Oh, I need to move fast. Okay, and so next system. I'm not going to go to the details, just for news, like the GIFs version 17, we're moving to the 9 kilometer in this plant implementation in 2025, 2026. We have run a set of the so-called hydrolution test. Maybe a sneak peek, but there's not much difference in the trunk among the coupled and uncoupled. Here, the version 16, the uncoupled. And the major issue comes with the coupled is the the weak intensity. But in the version 2, so-called HR2, we made some changes on the PPL and the convection. We improved the intensity, but it's still weaker than the uncoupled forecast. That's part of coming. I'll move to the ensemble forecast. Just that you know, has run a set of ensemble forecast prototypes as well, so-called EP4 and EP4B without aerosol radiation tracking. Overall, the trunk is compatible and improved compared to the current operation model. In terms of intensity, also the coupled prototype degraded intensity is except the very early time, and including the aerosol radiation tracking actually didn't change much in the intensity forecast, but it made the trunk forecast a little bit worse. But I stop there. That's all. That's our leave this slide here. Our next phase implementation plan.
Thank you, Fang Wei. That was a nice presentation. I think we'll also all be curious to see how those next generation GFS and GEFs perform for tropical cyclones as well. So now I have the pleasure of introducing Jim Doyle to give our next talk at the Naval Research Lab. Someone with whom I collaborated quite closely during my years at NRL before coming over here to the National Weather Service. So with that, take it away, Jim.
Yeah, thanks very much, Will. It's good to hear your voice. I wish I could be there in person, but it was really tough for me to travel this week. Just want to say a little background on this session that VJ and I and Linus at one of the IWTC meetings thought that there's a lot that we often learn from the forecast busts or difficult storms for the models to predict. And so that was one of the motivations for getting the group together occasionally to be able to talk about these. So I think it's a really great session. So we heard a lot about Philippe already, and I'll be presenting a bit more, a different perspective maybe from the COAM's TC side. So next, please. So Philippe was really a challenging storm. It had unusually high track errors. If you hit the next one, Will, it's much larger than the average for the Atlantic Basin. So it was certainly a major challenge. Next, please. And if we look at overall the scores for the different models, the track mean absolute error on the left and the intensity mean absolute error in the solid and mean error in the dashed, we see that there's a cluster of the high resolution models that use GFS or GFS based, including CTCX, which is in the solid blue line on the left. But then you can see HAFS-B and HAFS-A were quite a bit better than the other models. And one thing that stands out in terms of the intensity is HAFS-B was actually the best model for intensity as well. So there's a very strong correlation between, we think, in terms of the intensity errors and the track errors in this particular case. Next, please. So this is an animation. You'll see the little red dots trucking along, and the blue lines are the forecast tracks. And you can see there are several points in the forecasts of CTCX where there were particularly bad forecasts. And that was kind of common to the GFS-based high-res models. The black line and the green dot show the observed track and TC position. And overall, the message amongst these models, they all struggled. The early forecasts were too fast and gained too much latitude. During the middle of the life cycle of Philippe, forecasts erroneously recurved the storms, you could see at that point. And then forecasts made when Philippe was approaching the islands kept the storm too far east at that point. Once Philippe moved past the islands, the forecasts were really quite good. So we'll take a closer look at that. Next. And so this is looking at the point in that middle portion where the models recurved Philippe quite a bit. And this is closely linked to the erroneous over-intensification of the storm at this time. You can see the intensity on the right on all of those forecasts, incorrectly forecasted intensification. Next, please. And the HAFS-B forecast, on the other hand, was dramatically different. You can see the track forecast actually was quite good for this particular watch time. And you can also see the HAFS-B intensity forecast on the upper right was actually quite good as well, where all the other models over-intensified Philippe at this time. Next, please. And not only that, we look at our experimental 21-member COAM's TC ensemble that was run in real time. And this ensemble was fooled by Philippe as well. You can see that track forecasts all missed the boat on this and headed north as part of this erroneous recurvature. And you can see the spread and the intensities were all outside and above the best track in black. So it's really rare to see the validating track and intensity so far outside the forecast envelope. Next, please. So the question is, why does the 30th September 0Z CTCX forecast keep Philippe stationary in this case for about 36 hours, and then it starts moving north as part of that recurvature error? So there's a bit complicated, but Tropical Storm Rina, which was north of Philippe, was a contributing factor. The low-level steering flow at this time was easterly. In reality, the weak Philippe also was very poorly aligned and appeared to respond mostly to the low-level steering on the 30th and 31st. Next. And so CTCX intensified the storm to 70 knots. It became a well-aligned hurricane on the 31st and experienced the upper-level steering flow, which was westerly. And so it had the opposing steering flow influences of the easterlies and the westerlies and remained quasi-stationary at this time during this time period. Next, please. And ultimately, the storm in CTCX was able to move north through a break in the mid-level subtropical ridge. And so this is part of the reason for this erroneous northward movement. Next, please. And so underscoring that track's really highly sensitive to the intensity in that case in particular. Next up, another particularly difficult forecast challenge was Hurricane Otis. Next. Of course, this has been talked about quite a bit already, but all the high resolution models did very poorly, including the global models as well, in terms of predicting the intensity. You can see the intensity errors for Otis on the left, and the mean absolute errors in dashed are really poorly. This is none of the models were able to capture the really impressive intensification rate. The other surprising aspect is that track forecasts performed especially poorly in this case. The models didn't predict the landfall really until the 2406 forecast, about 24 hours before it occurred. Next, please. And this is just an illustration of some of those forecasts. The forecasts were too slow and left of track for CTCX. And the extreme RI was completely missed. And even as the storm was undergoing RI, the model couldn't keep up with that intensification rate. Part of it is resolution. CTCX is 4-kilometer resolution, but that's not the whole story here. Next, please. The ensemble as well. Most of the members take a track paralleling the Mexican coast, and all the members keep the intensity now below hurricane strength through the observed landfall. So another large bust for the 21-member ensemble as well. Next, please. And this is just one other forecast a little bit later. The track is reasonably predicted by the 12Z on the 24th initial time, but even the members with substantial positive intensity perturbations at tau 0 were unable to significantly intensify the TC. Next, please. So let me summarize two really challenging cases. Philippe is a really fascinating case study of the relationship between track and intensity errors. And Otis is a great test case for the ability of these high-res models to capture extreme RI. And it's also another case of perhaps related track and intensity errors as well. Next, please. But it's not all bad news because there were a number of storms. These high-res models, such as CTCX, did especially well. One of them is a high-impact case of Adelia, and you can see the track forecasts here for CTCX were actually excellent for Adelia and really nailed the landfall location and timing as well. You can see by those red dots in the inset compared to the green dot. It was, I think, quite useful in terms of the track forecasts. Next, please. And of course, intensity forecasts had handled Adelia quite well. And I'll stop there. Thank you very much.
All right, thanks a lot for that, Jim. Next one up, we have Michael Denard from the German Weather Service. Michael, are you on the line?
Hi, yeah, can you hear me?
Yes, we can hear you. Go ahead.
Good afternoon to everybody in Miami. Thank you for giving me the opportunity to update you with the work we do at the German Weather Service. Next slide, please. Yeah, I want to give you an overview on the tropical cyclone tracking that we do at DWD. It's a very simple tracker. It uses mean sea level pressure, just mean sea level pressure. The input fields are interpolated to a 40-kilometer ecostradal grid, which is a tracking grid, and we have a 3-hourly time stepping, and the tracking just looks for nearest neighbor matches. And I will give you an overview on the tracking products and what we can learn from it. Next slide, please. Here you see, oh, unfortunately, it's not really clear plot. Here you see strike probability maps. These strike probability maps you generate by choosing a fixed neighborhood for each grid point, and then you count the tracks which cross this neighborhood. So you get probabilistic transformation from the track distribution into a probability stuff. The upper left plot is a very small neighborhood. So you see there are very small probabilities. The legend shows you that the probabilities are below 10%. And you lose the tracks at larger lead times because the probabilities become very small. If you increase the neighborhood, you get more and more information on the track distribution. However, the lower right plot shows you, which is 120-kilometer neighborhood, which is the usual neighborhood that it is used commonly for constructing strike probability maps. There, in this plot, you have no information on the preciseness of the forecast, especially in the beginning. At lower lead times, at smaller lead times, because you always have 100% probabilities there, because the track distribution is much smaller than 120 kilometers. Next slide, please. Oh, I'm sorry. Okay, so I just tell you what we're doing here. I'm really surprised about that. No, it's. All right, it's completely destroyed. So what? No, there's just a PDF. Oh yeah, that's fine. That's better. Thank you. Next slide. Right, here we are. Thanks very much. So what would be the better option is to have an adaptive strike probability, so that the neighborhood changes along the track according to the distribution, the width or the range of the track distribution. So how can we do that? I tried a special way of doing that. What you do is you want to choose a neighborhood for the black dot on the model grid. So you can calculate the different neighborhood sizes and count the tracks or objects that are in there. Then next, you define a neighborhood, a larger domain of interest. These are the blue dots. And you do the neighborhood stuff at each of these grid points. So what you get at the end is number of probabilities in this domain of interest. And from these probabilities, for each size of the neighborhood, you can construct histograms. And if the area is, or the neighborhood is too small, you get the black distribution. So if the neighborhood is small, you get small probabilities and a high count of small probabilities in that case. If the area is too large, you get a high count of large probabilities, high probabilities, close to 100%, which is the white histogram in the back. And there's some optimum in between, which is characterized by the maximum entropy. And so what we do is, along the track, we choose the neighborhood with maximum entropy probability distribution. Next slide, please. So this is the result. If you look in the icon ensemble, you see the probabilistic information, or the tracks transferred into a probabilistic information, and you can see where the cyclones move. Next slide, please. And of course, I did this also. I did this with ECMWF EPS as well. So, and there's a striking difference between these two plots, because the ECMWF cones are much longer than those from the icon model. And the question now is, why is this exactly the case? Next slide, please. So for the next slides, we want to concentrate on the TC Franklin, which you see inside of the black circle. You see the very short probabilistic or cone or the short ensemble tracks, and the blue line is the analyzed track positions from the icon model. So there's the system should be able to forecast it, but it's not. Next slide, please. So here you see the reason for that. The left large plot shows you the sea level pressure minima, just the minima in red from the high resolution deterministic ensemble, deterministic forecast from the icon system, which is initialized by a 3D ENVAR analysis. And you see very nice tracks. On the right, you see the ensemble members from they are initialized by analysis states that come directly from the LATKF system at DWD. And what you see is that the tracks are very, very short, very noisy, and in addition, in the region where we expect TC Franklin, there are noisy bumps or stochastic patterns in a way. And the question is, next question is, where does these bumps, these stochastic pattern come from? Next slide, please. We skip this, go to the next. Thank you. The reason is we initialize from the forecast, the ensemble forecast from the LATKF ensemble analysis. And this is a square root filter which has covariance inflation techniques, because you have to stabilize the filter variance during cycling. And there you have multiplicative factors, you have additive inflations, you have relaxation to the prior methodologies in there, but also SST perturbations. And these stochastic patterns we found there looked like some SST perturbation patterns. So we did an experiment reducing the amplitude of the SST perturbations by a factor of 10. Next slide, please. And here you see the result. On the left, you see the IFS, operational IFS system from ECMWF, and nice, beautiful long tracks. This is the upper left panel. But also what you see is that there is some disturbance after 48 hours, exactly when the icon tracks, ensemble tracks, stop and do not continue anymore. This is the middle upper plot. And the red line is the deterministic high resolution track. So you see, in principle, the tracking works very well if there is some row or some row of sea level pressure minima. And on the right, you see the experiment with the reduced SST perturbations. And the system performs somewhat better, but there's still a large difference to what the ECMWF tracks are showing. Next slide, please. So the go-home message from this slide is just the icon EPS initial conditions seems to be suboptimal. There is also involved in recentering from the LATKF perturbations to the high resolution analysis, and this is only done halfway. So it seems to really a problem there, which is caused by these stochastic perturbations. A similar thing is found in the JEPS system of the Canadian Met Service. But I'm not really sure if this is the same reason. Next slide. And this is my last slide. The question now is, what can we do? So we found that the LATKF analysis are suboptimal to initialize ensemble forecasts. So we need a different ensemble analysis data assimilation system in a way. So Met services, other Met services, they go for ensemble data assimilation using 40 VAR or 40 ENVAR analysis with different data sets that are generated by perturbing the observations. this is a very costly way of doing it. Especially in the ICANN system, we do not have a 40 VAR system because we have no linear and adjoint model versions. So yeah, but an 40 EN-VAR is under development, so we could go for this option. However, yeah, adapting noise by costly minimization of different analysis ways is a really expensive thing, and I don't know if we can afford this. So I'm working on an alternative way of doing that using singular vectors. This is the second point on that slide. What you do is you send us a singular vector calculation on the assimilation window, and try to find the singular vectors that where the trajectory deviates from the reference, which is the black horizontal line at the bottom, and approaches to some target which represents the observed state or observations in a way.
Looks like we're about out of time now, Michael.
Right, I'm fine, almost fine. Just want to mention that singular vector is also very costly, so it's not really an alternative at this point, because any new singular vector needs a full model run, and the plan is to replace the model by machine learning, data-driven models. Thank you very much.
Thanks a lot, Michael. It's very interesting to see what the German Weather Service is doing in terms of tropical cyclone prediction. And last speaker of the session, I have the pleasure of introducing Sharon Majumdar of the University of Miami, who's also my former PhD advisor several years ago. So take it away, Sharon.
All right. Yeah, thanks very much, Will. Actually picking up a little bit from where you left off for your PhD here. Apologies, I've got a bit of a cold, so I'm a little bit raspy here. This represents research done with Linus Magnusson of ECMWF, and you'll see a few things related from his talk. How do I advance slides on this? The big green arrow. Okay. Big green button. All right, what do I point at? Ah, the big green button, yes, not the little green button. Okay, sorry about that. Okay, so the main question that we're asking here is which cases were particularly difficult to predict? And our ensemble forecast of choice here is ECMWF ensemble. So here's just a picture to motivate the problem. That actually neither of these were difficult cases, but just to show the problem here. This is a 7-day ECMWF ensemble forecast. This was initialized before Franklin or Idalia had formed. And we see that there's quite a few ensemble members for Idalia and for Franklin here. And the white circles that represent a disk of radius 1,000 kilometers around the location at the time that Idalia and Franklin were tropical cyclones at the verification time. So the method that we use here is the 50-member ensemble forecast. And we look at a series of forecasts initialized from 240 through to 0 hours prior to the verification time. And one can verify in different times here that actually what we're going to use here mostly is when the storm was named as a tropical storm. One can also verify the census time or when the storm was 50 knots or others too. And we also, from this, calculate the probability that the tropical cyclone is predicted to lie within some distance, that is within that white circle on the previous slide, of the verifying location. This is all based on the ECMWF tracker, and I should point out the results are very sensitive to the choice of the maximum wind speed that's in the model output. So here's a diagram similar to what Linus showed earlier. This is just to show, this was Lee, and the verification here is at the time just after Lee was named as a tropical storm. And so we see here that 10 days prior to Lee being a 45-knot tropical storm, that probabilities are very low. And these probabilities, as one might expect, would increase with time, and not always monotonically, as we see here. Now, what I want to draw your attention to here is the time, the lead time at which the probability drops below 25%. We're just going to look at the orange line for the purposes of this talk. And so the orange line represents a sort of distance tolerance of about 1,000 kilometers. And so we notice here that the probability drops below 25% for the first time about 204 hours prior to this time that Lee was a tropical storm. So this is just kind of setting up the problem, and then we do the evaluation for many storms. So this is all very subjective. The way that we evaluate it is that we take a 25-knot model tropical cyclone for each ensemble member, and we identify whether it exists within 1,000 kilometers of the location at which, at the time that the actual tropical cyclone was named. And then we find this time beyond which the probability first drops below 25%, as we showed with the Lee case. And totally subjective, we say that if this time is shorter or equal to 4 days, then we call that a difficult case. We also do the same, but then here we say, well, if the storm has reached, for cases that reach 50 knots, we deem it a difficult case if it's not even captured as a 25-knot model tropical cyclone. So this is just a very subjective way to identify. You know, we're trying to give the ensemble a chance to sort of capture a tropical cyclone and many of its members, but if a 25-knot model tropical cyclone is not really existing in most of the ensemble members less than 4 days prior to it being a 50-knot storm, then we've got issues. So here's the case with Lee, just repeating the same figure from before. And so here, this is actually a fairly straightforward case that this time is 204 hours. However, let's look at Laura. For Laura, we see that the probabilities are more or less zero with a 7-day lead time before Laura got named as a tropical storm. And then the probabilities increase quite substantially, up to nearly 80% here, with a 4-day lead time. And then the bottom completely falls out in this ensemble forecast, that we find that the probability drops down to less than 10% when there's a 60-hour lead time. And so that is the lead time that is here and is deemed a difficult case. We can look at the fields here. We'll look at 84, 60, 36, and 12-hour lead times. Just show some of the fields here, just for the deterministic forecast, but you can imagine that many of the ensemble members were similar. So here's the 84-hour lead time, and so it looks like a tropical cyclone in a deterministic. I'm slightly off position, but the left-hand side is 850 millibar vorticity and geopotential height. The right-hand side shows so closed MSLP contours, and the convective rain rate is plotted for reference too. Look at the 60-hour one now, that it's barely even an open wave in this forecast, and these are all valid at the same time, that when Laura was named tropical storm. This shows some of the inconsistencies in the deterministic forecast as well as the probabilities. 36 hours slightly recovers, sort of a bit of a closed low here and there in the deterministic. And then 12 hours prior to Laura being a tropical storm, we see that there's something that looks like a tropical cyclone. So now let's just look at all of the cases together. So here's our sample. We're only including storms that made it to 50 knots here at some point in their life cycle. And in 2020, we're just going from Gonzalo onwards. So here's our sample, and we should know also, I think Linus mentioned this too, that the ECMWF ensemble its resolution was 18 kilometers until June this year, and then it shifted to a 9-kilometer resolution, which might be important in the results here. So here are the cases now that we deem difficult using that rather subjective metric that we defined. So in 2020, there were many difficult cases here, and I'll show plots of them in the next slide. Most of the cases were difficult. 2021 and 22, about a third of the cases were deemed difficult here. Some of them, fairly not terribly significant storms. Then there were some, and it's probably going to be discussed quite a bit at this meeting, was cases such as Earl and Fiona, which were quite heavily sampled with the aircraft before their genesis, and so those were deemed difficult here. A look at 2023, only one case, Ophelia, which was a tropical transition case. So here are just those difficult cases plotted. The colors are by year, and then the shapes by the genesis process. I just took the NHC reports for each of the storms and then just sort of loosely classified the genesis process based on their reports. So it's pretty interesting here. It's like, if we look at a lot of the blue circles, those are 2020 cases, and some of the Greek storms there in the Caribbean, some of the, it's Laura and Marco in the Gulf of Mexico and in the Atlantic. So 2020 was a really troublesome year. We see a few of the squares in the central Atlantic. Those are more sort of broad circulations, and it took a long time for convection to organize. Then we have a few tropical transition cases as well. We see at some of the latitudes from 25 north and above. It's really interesting that 2023 only had that one case, the tropical transition of Ophelia. So yeah, I don't have much to complain about for 2023 with the CMWF ensemble for formation. So just wrapping up, we need to investigate further why the difficult cases were difficult. Wondering whether the ECMWF ensemble has been improving over the last 4 years, or whether it's just been kind of the types of tropical cyclones that developed, and maybe just the intrinsic predictability of many of the cases in 2020 was just lower. We'll plan to create reliability diagrams and other evaluations for developers. We'll also include non-developing disturbances. Two of my PhD students, Quentin Lawton and Will Downs, are developing trackers for research, and so I'd like to include those in the evaluation too. I would like to compare these with the NHC outlook probabilities, and then also investigate the flow regimes of relatively low predictability, not just for genesis, but also for the early intensification. And I must be out of time, so I'm going to stop. Thank you.
Yeah, thanks a lot, Sharon. Very well timed. I guess right now we have time for some Q&A and discussion. So would you like me to?
Got about 18 minutes.
Well, maybe since I have the mic in my hand, can I start out with a question for Sharon on his talk? I was just wondering, you had the 3 genesis mechanisms. I noticed that you had weak wave on there, but not specifically strong wave or easterly wave. Is that just because those cases are not difficult cases in general?
Yeah, that's correct. The ones that were weak waves were essentially... Yeah, thanks, Ray. Sorry. Yeah, the cases that were weak waves were mostly African easterly waves that then really became very diffuse by the time they had reached the Western Atlantic or the Caribbean. There were no strong waves there, the strong African easterly waves at all in our subjectively classified difficult cases.
Okay, great, thanks. Start with some comments and questions in the room before we go online.
There was a couple of questions.
I got a follow-up to the same issue.
Yeah, go ahead.
Yeah, just real quick, Sharon, how do you capture cases where the ensemble's predicted development and there wasn't one? Is that captured in your statistics?
That's also yeah, that's going to be the next step. So a couple of my students have tracked at least just tropical waves and African easterly waves for those cases. And we can also build in inverse from NHC and just anything that was identified in the outlooks. And so I've done some evaluations for those, but just for 2020 and 2021. And there are some cases that the ensemble does sort of get a little bit too optimistic, and there are high probabilities, but yeah, not too many. The ECMWFs generally, I would say subjectively, not producing too many false alarms.
I see we have a question from Pete Black. Pete, I don't know if you have a microphone right now and if you'd like to just read off your question yourself. It seems to be directed mostly to Jim Doyle. I saw your face came up, but I don't hear you yet.
Yeah,
Yeah, go ahead.
I just, to cut it short here, Will, and directed to Jim at the moment, but we're just wondering why nobody have used a couple modeling tools to investigate the ocean impacts for the storms in the East Pac this year. There's a recent paper that published by a couple of colleagues in Taiwan, Ian Fei Kun and E. Lin, that talk about a similar situation in the East China Sea, where normally cold SSTs were quite warm this year, greater than 30 Celsius, the same thing. Same situation appeared to exist in the East Pac off the coast of Acapulco. So I'm just wondering why nobody's been looking at the possible impacts of ocean interactions there. That's an area where the so-called Toronto peckers form, where you have warm and cold eddies adjacent to each other that are formed by strong winds coming through the Gulf of Tehuantepec gap there. Oh.
Hey, Pete, good question. We haven't explored that yet, but we've talked about it. The SSTs, like, for example, the Otis storm, that was the big forecast bust in the East Pac, and there are several in the East Pac that were challenging this past year. May have had a component related to the especially warm SSTs in that area. So I think that's a reasonable point. I think my opinion is it's part of the story, but not the whole story, especially with the Otis, of why the models did so poorly. I think there might be some other environmental conditions that might be a factor. But it was certainly a small storm too. A lot of the East Pac storms have been relatively small RMWs, which are challenging for the storms to be able to resolve those really small inner cores too. But yeah, air-sea interaction, the upper ocean, I think definitely is a factor.
Yeah, Jim, I'll put the info from this paper from Westpac in the chat here, and maybe we can talk about it later on.
Okay, great.
Dave,
Thanks,
I don't
Pete.
know if you had a new question or if you were going to follow up on that one.
It's a new question.
A new question. Okay, well, I just wanted to respond real quick to Pete. Just to mention, like in cases like Otis, it seemed like the SSTs were, from what I can recall, quite favorable. So I think in this case, a lot of the East Pac storms SSTs are not a limiting factor for RI, and it's more like if SSTs are already favorable, you know, why did the RI occur anyway, or why does it not occur in some cases? So I think it wasn't really a case where there was a lot of uncertainty with the SSTs, at least from what I've seen. So
yeah, no, they were pretty well known, I think, and it was persistent throughout a good part of the season as well.
Yep.
But it's just that the season would seem to be an anomalous structure sitting out there waiting for something to happen.
But point well taken that we don't want to forget about the SSTs when we're talking about predictability. So yeah, thanks for that. And so we got another question in the room here.
Yeah, so it's more out of curiosity. Has there been any evaluations done with regards to the post-landfall and how they have transitioned into extratropical, or how it has sustained itself post-landfall, and what has been the overall performance?
This is for anybody, right? Yeah, that's just for all the. Anybody look at a post landfall? Linus.
Or rather extratropical transition. No, there only case of them I've been looking into the details is what happened with Tropical Cyclone Franklin, and the uncertainty injected in the mid-latitude was quite astonishing. It's probably the largest growth of forecast uncertainty I've seen in these type of cases. So that's in terms of extratropical transition, a really interesting case.
Okay. Any other comments on the?
Jim Doyle has his hand up, I
Oh,
think,
go
to
ahead,
respond.
Jim.
Hey, I think this is a good question, and we haven't done a systematic evaluation of the landfalling storms, but we've looked at a few in quite detail, including Adelia. And there's definitely some challenges, at least with the CTCX model and some of the landfalling systems and the ability to produce relatively high winds initially after landfall seems to be a challenge. And I don't know whether that's a challenge for other models as well, but I think transitioning from the relatively smooth ocean surface over the land surface sometimes is a hard challenge for these storms to make.
All right. Thank you, Jim. I was going to go to a question online next. Castle, would you like to read out your question, or would you like me to read it for you?
No, I can read it. It was really fascinating to hear all the various challenges, the forecasting and modeling challenges you highlighted. I'm curious that given those challenges, what would you say is the single most important research priority that deserves more attention?
Anybody on the panel? Go ahead. Linus.
Yes, or at least for this community, the question I raised in the end of my talk for the RI, what distinguish a case that the current models are able to predict with the cases that are currently out of reach? At least for me, that's an open question to know which cases can we do and which we cannot do, and is it anything beyond just the size of the cyclone in that respect?
Go ahead, Jim.
Yeah, that's a good one, Linus. I was going to bring up a similar point. Some storms like Adelia, the high-res models seem to do exceptionally well at. Other storms, Otis, and there's plenty of other ones are challenges. The other class of storms I'd like to bring up are those storms that are undergoing moderate wind shear that still end up aligning vertically and undergoing rapid intensification. And the models really struggle with those storms. I think there's a lot going on in terms of the environmental interactions and being able to accurately capture the alignment process seems to be really key to be able to predict the onset of RI, which is the hardest part of predicting RI. I think Michael Fisher's done some, Rob Rogers and others have done some really nice work related to this, and I think there's a lot to still unpack related to trying to predict these storms.
You want to put a plug in for TCRI, Jim?
Yeah, sure. Why not? Thanks, Frank. Yeah, so this is one of the focus areas for the ONR program called Tropical Cyclone Rapid Intensification. And the group decided that one of the hardest problems is to be able to observe and predict the onset of RI. So we spent quite a bit of efforts in our observing part of this project, to working very closely with the NOAA HRD AFEX program, and trying to observe and get some observations at the early stages of RI, which is, sometimes these storms sit on a knife edge and they could go either way. So being able to get more observations into those systems is, I think, really helpful.
Okay. Let me bring it over to, oh, you already have a mic. Okay, Chris Lancy.
Yeah, question for Julian. Noticed in your talk that for the Northern Hemisphere track errors, you've shown no improvement in the UK deterministic model for almost 10 years. So the question is, what's your interpretation of that? Why haven't we seen any improvement? And is there any implication for the future for track predictability?
Yeah, I think this one comes up quite frequently over whether we've reached the limit of predictability. Interestingly, if you look at the equivalent plot for the southern hemisphere, then there is still a downward trend in errors. So I guess the question is it regionally dependent? But yeah, it's a good question. I mean, the last time we had a significant improvement in intensity was a real a kind of one-step thing, which happened about, as you say, almost it's about 9 years ago now, and that was due to a completely new dynamical core in the model. So I think there's not an improvement going on at the moment, but we haven't actually made any model changes, really major model changes in the last few years. Now, there's in the next 5 years, there's certainly with the Met Office model, there's going to be some major changes because basically the whole thing is being rewritten, new dynamical core, a new kind of a whole structure of the storm. The model is different. So once we get to really testing that, it'll be interesting to see whether there is any scope there to capture a bit more improvement in track errors, or whether we actually have reached the limit of predictability, whatever you do to your model. So it'll be interesting to see how that pans out in the next few years.
All right, yeah, thanks for that. We'll move on to the next question.
I want to go back to the Otis one. If you look detail of the ocean part SST forecast is pretty good, and the real problem is the storm going to the wrong place, so that causes the rapid intensification doesn't happen. So that is one comment I want to make. Then another thing is about the landfall storm. I think we, as a community, we need to do further on the landfall storm. That's the people feel the pain of the storm. Because if the ocean, yes, from scientific point of view, that's great. We're doing those science understanding. But in the meantime, if we want to see our value of the forecast, we need to focus on the landfall storm. Like this year, I showed the Doksuri in hit China, that right hitting all the way from east coast all the way to Beijing. So that caused like in one day, the rainfall is almost 150% of the whole year rain in Beijing. So that's people can feel. Same things here. If not hit land, our science not showing the value. I think it's also and NWS should do that kind of research to showing our forecast value.
Yeah, those are all good points. At least from what I've seen in case studies, it does seem like people tend to focus on the landfalling storms, but I agree that those are the highest impact. So, further work needs to be done.
Yeah, I think there was a couple talks, maybe Julian's and some others, where you're showing biases, overall biases, and again, there's 100 ways to slice and dice verification. So you might have done this, it might have been a slide and catch it. But I find with biases, it makes a big difference to stratify from initial intensity. And I remember in my study back with HWRF years ago, it's the initially strong storms, hurricane force and above, had a positive bias, and the ones that below hurricane force had a negative bias. And I think there's obvious reasons for that. And I think it's important to at least always stratify by initial intensity to kind of churn out some of the gold in the results.
Comments from the panelists?
We've got time for one more short question if there's any others out there. Kate, did you? Oh.
Well, 30 years ago, the limits of predictability was brought up, and there was like even O&R funding to prove that we'd reached the limits of predictability with track. So I find this kind of interesting, but the consensus errors, even in the last 5 years, have been going down, and all the basins. And at the shorter range forecasts, we're kind of plateauing more than we are in these longer range forecasts, like out to 5, 6, 7 days. So I think there's still room for improvement and track error in the models.
Go ahead, Jim.
I'll just make a comment on that about the predictability, and it's a pretty tough, predictability limits are a pretty tough one to nail down, and almost all the estimates of theoretical estimates of predictability and predictability limits, even by Lorenz, have to some degree have not panned out, and we've been able to push beyond those. And so it remains to be seen how far we could be pushing the models and our forecasters, and how far we can go with track forecasts and intensity forecasts. But I think I'd like to think positively that there's more room for improvement. I think, especially if we're thinking of probabilistic methods as well.
Thank you, Jim. I want to thank all the presenters in the previous session for your time. And we're going to go ahead and take a 15-minute break and start the next session about 4:15. Thank you.